Hello. Today we will be talking about geometric nonlinear analysis. We'll make a brief introduction to geometric nonlinear analysis. So before moving forward, first I want to discuss our main assumptions in the first order analysis, which is the analysis that we have been performing. It's linear analysis. Now in the first order analysis, what we were doing is assume that I have a cantilever like that, has a length equal to L, and under the effect of an axial load P and a vertical load F. So what we were doing is we were looking at this picture, at this structure, undeformed shape, and we write our equilibrium equations. So we are saying that the equilibrium equations are written with respect to undeformed configuration. Okay, so I'm looking at this picture, I'm saying that, okay, I have P here, F here, and the moment is equal to F times L. The other thing that we say is under these loads, the structure deforms, right? We will see some deformation here. And again, we calculate the effect of the loads just looking at the undeformed shape as well. So we say that the effect of loads are considered according to the undeformed configuration. So basically what we are assuming here is the nodal displacements and rotations are small. Or let's just write it as small displacements. That's what we were assuming. So here we are saying that this delta is so small that moving the loads from here to there doesn't make much of a difference. And again, writing the equilibrium equations according to this configuration doesn't change our results much. This is what we are assuming. Okay. We also have other assumptions. We are saying that strains are small as well. So in other words, we are saying that there's a linear relationship between displacements and strains. Basically what we are doing is we are using the engineering strain definition. It's the simplified version of the actual strain, of the true strain, and in a very simple way we are saying that strain is equal to deformation divided by length. Or for an infinitesimal element, we write the strain as du over dx. And again, we say that the strains are small, so we can say that the bending, shear torsion, and axial deformations are uncoupled. We are just examining them as if they don't interact with each other, right? So we are just take a section cut somewhere here, and maybe let's just show it for a simply supported beam, it's easier. So for a simply supported beam, let's say that I have F here and P here. We take a section cut, and then we write our equilibrium equations again by considering the undeformed configuration. We have a reaction force, we have P and the moment, and the moment equation is m over EI will be our curvature is del square y over del x square, y being the transverse displacement. So that's the bending deformation, no effect of the axial load or no effect of shear deformation, and we say that the axial deformation is P is equal to EA over L times the amount of shortening. So this is the equation for axial deformation. So we ignore the interaction between the axial and the bending deformations. The other thing that we say is length, area, or any other sectional properties doesn't change with deformation. They don't change. So we are using the initial length, initial area, and everything. So here, what we are assuming is deformations are small. So with these assumptions, we were able to perform a first order analysis, a linear analysis, and that assumptions really simplified our solution. Now let's take a look at the second order analysis, or I would say geometric nonlinear analysis. Sometimes it's also called the second order analysis. Now again, I want to work on this cantilever example. So we have P here and axial load F here. Now in that case, equilibrium equations are written with respect to deformed configuration. So that's why the nonlinearity comes from, because at the beginning of the solution, we don't know how the structure will deform. So we have to perform a linear solution first, get the deformation, rewrite your equilibrium equations, and continue this way. Okay, so we know that under these loadings, the structure will deform as follows. So we will have some displacement delta, vertical displacement here. And if I want to calculate the support reactions, now I have again P, F, but this time the moment will be equal to F times L plus P times delta. So as you see, when I write my equilibrium equations, considering the deformed configuration, I obtain second order forces, second order moments. Now, the other issue is, as in this case, loads can move according to the way the structure deforms. So in other words, I actually move the loads here and rewrite my equilibrium equations. That's why I was able to see the second order moment due to that axial force. So these are the things related to the equilibrium equations. Now we also can consider the coupling between bending, shear, torsion, and axial deformations can be considered. So for the simplest case, again, let's take a simply supported beam. Right, let's give some initial crookedness to that simply supported beam. Let's say that it's not perfectly straight, and I have some initial crookedness here, and let's apply an axial load. Okay, and now again I'm taking a section cut here, and I'm writing my equilibrium equations, but this time using the deform configuration. I have an axial load P here, and then internal moment. If I take moment with respect to the pin support, I obtain the following equation. Del square y, del x square EI minus P times y must be equal to 0. So as you see, the axial force will, in that simple equation, we see that axial force can increase or decrease the curvature, or in other words, the bending deformation of the beam. So in other words, with this simple case, we consider a coupling between the bending and the axial deformations. And you can also find out other ways to couple in your formulation, shear, bending, and maybe all of them. So this is what we do in the geometric nonlinear analysis. The other issue is effect of finite deformations. So we no longer say small deformations, of finite deformations. So in terms of deformation, we can consider large strains. We can consider the change in length and or area in our strain definitions. Okay, if you do that, we are considering finite deformations. And instead of saying small deformation, we can consider finite displacements. When we say finite displacements, we also mean that we consider rigid body translations and rotations in our formulations. So for that, we can use this simple example. Now let's say that I have this structure. I have a weight at the middle, and I'm connecting this weight to these two cables. Okay? So if I do first order analysis, the first order analysis will tell me that the structure is unstable. But I know that if I consider the finite or the rigid body translations and rotations in my formulation, again I can keep the deformation small. I'll see that the second order analysis tells me that as the structure deforms, it finds a stable configuration and can carry this applied weight. Reaches to stable configuration as the structure deforms. So these are some terminology in the geometric nonlinear analysis. Basically, we are writing everything in the deform configuration, all our equations. And of course, you can increase the level of detail. You can consider the length or the area or the sectional properties in the deform configuration, assuming that your deformations are large as well as your displacements. You have to consider the effect of deformations on what your loads do your structure. You can just consider some of them. For example, you can say, okay, I'll have large deformations but small displacement, or the other way around, or you can just say that I only want to consider the effect of loading in the deformed configuration. So with these combinations, you can perform the different geometric nonlinear analysis by considering different level of detail. Now, when you do a geometric nonlinear analysis, you may see different types of load deformation curves. So let's work on that. Let's see what we can see when we perform a geometric nonlinear analysis, because our nonlinear solvers should be able to handle these type of curves. Okay, so of course when you do the first order analysis, everything is elastic. Let's start from there. The same structure, we do a second order analysis, but as the displacements or the deformations increase, it deviates from the results of the first order analysis. Okay, and then it may reach to a point where the slope is 0. So we call that point a limit point. This doesn't mean that the analysis ends here. Okay, the deformations can continue. Okay, and it can find another equilibrium point. So we have to continue, we have to figure out the full deformed configuration, deformation path of your structure. And at some point, you may see a branching. Let's show a branching here. Okay, so the branching means that there are two equilibrium paths. So both paths, both type of deformation satisfy the equilibrium condition. So these type of points are called bifurcation points. Should have an R here, bifurcation points. And I can see stiffening due to the deformed configuration, or I can see softening. And after a certain point, I can of course see a failure point. So basically, when you perform a geometric nonlinear analysis, you can see all sorts of complexities. You can see softening, you can see stiffening, so your solver should be able to handle both of them. You may have a limit point. Limit point means that your stiffness matrix becomes singular, so you should be able to solve singular matrices. And the most challenging one is the bifurcation point. So you have two equilibrium paths. Which one to follow depends on your solution algorithm. It doesn't know whether it's a bifurcation point or not. It may continue this way, or another solver may continue that way. That's the most difficult point to catch in an analysis. The actual structure, which path does it follow? Follow the path that has the least energy, or we also say that that's dynamically preferred. Okay, so these are some points, and our solution algorithm should be able to capture that. And let's write the definition. We see the bifurcation point is the point at which two or more equilibrium paths cross. So which one it follows? The structure takes the path that is dynamically preferred. Now we have a limit point at which is the point at which the tangent to the equilibrium path is horizontal. Zero stiffness, in other words. We have a failure point. The point at which a path suddenly stops or breaks due to a physical failure. Okay, so basically in a geometric nonlinear analysis, we want to trace the full load deformation curve so that we can see what's going on with the structure. Okay, whether do we see some instability during these deformations, or the structure is fully stable? Do we reach any bifurcation point that we missed? So these are the questions that we should be asking ourselves. And really, this is not the only type of load deformation paths we see. We also sometimes observe more complex responses. Let's also define them. Again, let me draw the load deformation curve. Now, the structure starts to deform and then it reaches a limit point. After the limit point, the structure is unstable now, and then it takes off dynamically. But as it continues to deform, it may reach to another limit point, and it may find a more stable secondary equilibrium path. Okay, so between these 2 points, we have an unstable structure. And here the structure dynamically takes off. But as it continues to deform, it catches another limit point and becomes stable. It starts to carry the applied loading again. Okay? And then, after that huge deformation, it finds enough resistance to carry the full loading. So this type of behavior is called snap-through response. Where do we see this type of response? Basically, one example is the buckling of shells. You can actually observe this. Take a Coke can, press from the side, and then you will see that it flips and it catches another equilibrium path and starts to carry the applied the pressure that you give with your finger. Okay, so if you just draw it, so initially it was like that. You apply some loading to it, okay, and then it deforms. So this is our initial stable geometry. It deforms, but after a while it loses its all stiffness. It becomes unstable. It dynamically moves, it flips, and then it catches another stable deformed configuration and starts to carry the loading. So initially it was under compression for the loading, and then it buckles, but after the buckling it catches another stable geometry where it resists the applied loading with tension. Okay, so in other words, this is what we see. You apply the compression, we have the compression, it softens and it limits, and then it buckles. With the buckling it continues to deform. Now it finds a second stable geometry. It can carry the applied loading with tension, and then it can continue all the way. Okay, so this type of behavior is called snap-through response. There's another response. Let's draw the load deformation curve for this response. Again, we start with a stable geometry and then we reach a limit point. The structure becomes unstable, but it moves towards back, and we see a inflection point, and between these inflection point we see some stable behavior, and then another inflection point. It becomes unstable again. Now we see a limit point and then a stable behavior. Okay, so basically up to the limit point we have a stable structure. Between the limit and the inflection point we have an unstable structure. Two inflection points again stable, continues to carry the loading. Now it becomes unstable again, and finally it finds a stable deformed geometry. This response is called a snap back response. And we see this response usually in the cracking of concrete. So we can have a very simple load deformation curves, but at the same time we can have very complicated load deformation curves. So everything depends on the level of detail that we want to calculate, and of course what we want to see. Now I would say let's go over the sources of nonlinearity. So depending on what we want to observe, we can do our formulation accordingly and perform our analysis accordingly. So we say that one of the sources is the large strains. You can have small deformations but large strains. Okay, imagine that you have a rubber and you just apply an axial load. The displacements are small but the deformation is large. Okay, so but what is the limit between small and large strain? So we say that the strains are may be large, so over 5%, and we can see that in rubber-like structures. Or if you want to see the full yielding of steel, it deforms more than 5%, so we can just argue that it's a large strain problem. Why 5%? Now we will see different strain definitions, and up to the 5% strains, they more or less they give almost the same results, but after 5% they start to differentiate. Okay, so that's why if your strains are smaller than 5%, it doesn't matter which strain definition you use, the difference will be very small, maybe negligible we can say, but after that result starts to change. You may have small strains but finite displacements or rotations. And we can say that we have the cables, arches and bars, for example, that undergo very large displacement, but the deformations may be small. Or you can just want to consider the buckling effect, right? The loads, the effect of the loads change, right, due to the deformations. Again, when you have compression and when the compressive forces couple with the bending deformations, they tend to increase the moments in your structure, and the internal moment, if the internal moment cannot resist the moments due to the compressive forces, your structure buckles. And this may be the only effect that you want to see, and you perform a buckling analysis for that case. So we say that may occur even the strains and displacements are infinitesimal. Due to initial stresses. Okay? And there are two analysis types that we usually see, especially in the commercial softwares. P large delta effect, and we have the P small delta effect. Now for the P large delta effect, we use an example of a cantilever. So we have an axial load on it, and we have F. Okay? Now in that case, it deforms this way. This is delta. This delta may be too small, maybe a very small number, small deformation like we see in the building structures, but P could be very, very large. Okay? So even if delta is small, since P is large, the P times delta creates a secondary moment that you cannot ignore. Okay? So this effect is called P large delta effect. And we also have the P small delta effect, and for that we use a simply supported beam. And you may have some loading on it, and due to that loading you will see a bending deformation like that. That's small delta. And P times small delta, again the small delta, it could be very small, but P could be very large, and P times small delta may generate large secondary moments. So this effect is called the P small delta effect. Okay, so basically for the P large delta effect, this is what we assume. We only consider the translation of the nodes. In other words, I'm assuming that this translation is linear. Okay, that's P large delta effect. And if you want to add the deformation, that will be the small delta. You have to consider the small delta, and this is what we call the P small delta effect. When you combine them, you will have a geometric nonlinear analysis, but some softwares do consider only the P large delta effect in the geometric nonlinear analysis. In other words, they just assume a linear deformation and just calculates the effect of nodal forces. These are of course approximate geometric nonlinear analysis, but they sometimes work very well if your displacements and strains are very small. Now what we are going to do is, up to this point we see formulation with respect to the first order analysis, and we will just step by step break these assumptions that we make and work on the formulations, how we can break this simplified assumptions and perform a geometric nonlinear analysis, develop our elements accordingly.